So the reason I had that silly but awesome video is because the way dominoes fall is kind of the way induction works. When you set up a row of dominoes, you knock the first one over, and you assume that the first one knocks the second one over, the second one knocks the third one over, and so on and so forth. So there's a nice analogy between the principles of induction and the idea that dominoes work by you're able to knock the first one over, and if you're able to knock down, say, the kth domino, then the k plus first one also falls down. And that has a nice little analogy to induction, which is what we're talking about in this video. Chapter 4, 4.1, Mathematical Induction. And you might notice I'm using a little bit different format for the notes. I might ask you all in a little mini poll sometimes which you prefer, if you like the more traditional PDF printable notes, or if you like it more in this kind of, not a PowerPoint, but a PDF slide format. So we're trying something different. So let's start out by defining what an inductive set is. So a set T, actually let me turn on my pointer. There we go. So a set T that is a subset of Z, we're always dealing with subsets of the integers, is an inductive set, provided that for each integer k, if k is in T, k plus 1 is in T. There's that analogy with dominoes, okay? This is like saying if the kth element falls down, the k plus first element will also fall down. So I want us to think about, and this is a case where I'm going to ask you to pause the video and try to write this out yourself before I do it. But we want to carefully explain what it means to say that a subset of T is not an inductive set. And that description should use an existential quantifier. All right. So go ahead and pause the video, think about what that means, and then when you unpause it, you'll see what the answer is. And so here's the answer. So this kind of goes back to the stuff we're doing way back in chapter 1. Okay, so let's just go through this slowly. So here's the original statement. T is T subset of the integers, starting out with T subset of the integers, is an inductive set provided that for each integer k. So when you negate a universal, that becomes an existential. So if there exists an integer k, and here I have a conditional, so I have to negate that conditional. So what I want you to remember is the following, that if you are negating something of this form, for all x, p of x implies q of x. How do you negate that? That becomes there exists an x, not p of x implies q of x. Then you have to remember how to negate a conditional statement like that. And you do that by assuming the hypothesis and the opposite of the conclusion. Okay? So this is the answer to that first part A. This is what it means for a subset to not be inductive. That I'm able to find a k that's in my set, but the k plus 1 element is not in my set. All right, next thing we're going to do is use this definition to determine which of the following sets are inductive and which are not. So we're not going to worry a lot about formal proofs, but if it's not inductive, explain why. Okay, so the first one we're going to look at is A. Okay, A is going to be 1, 2, 3 through 20. Okay, so can this be an inductive set? Well, 1 is in there, and then 1 plus 1 is in there, 2 plus 1 is in there, and so on and so forth up to 20. So think about what goes wrong there. Okay? We have that 20 is in my set, but in order to be inductive, if k is in there, k plus 1 has to be in there. Well, 20 is in my set, but 21 is not. So A is not inductive. So this is not inductive. So because these are actually separate slides, I lost my not inductive, so I'm just going to put no right there for the first one. Second one, the set of natural numbers. Well, is this an inductive set? Think about it. Think about it for a couple seconds, and then we'll, if you think about it, you'll see that it is. It has to be, right? Remember the definition. If k is in the set, k plus 1 has to be in the set. Well, for any natural number you pick, if you add 1 to it, you're going to get another natural number. So yes, this one is inductive. And I'm going to lose my no and my yes on the next slide, but I will draw them back in. So we've already said that no, not inductive, yes, inductive. Now this one's a little more interesting. So this is a subset of the natural numbers, and I'm starting at 5. So this is equal to 5, 6, 7, and so on. Now, you might think that, it doesn't include 1 or 2 or 3 or 4. That doesn't matter for it to be inductive. All that matters is if I start with something in my set, if I add 1 to it, will I have something else still in my set? And I will, because the smallest thing I can start with is a 5. But if 5's in there, so is 6, and so is 7, and this goes on forever. So yeah, this is an inductive set. So yes. Oops, can't write with a pointer. Yes. So we've already said no, yes, yes. And this next one, I'm going to let you think about that one. And the same thing for all of these other ones. Pay particular attention to these inequality signs, because that matters. Okay? Pay attention to those inequality signs when you're trying to decide whether or not those are inductive sets. And now, as indicated on the slide, this does come from your book, page 170, 171, so you can look in there to get the answers to. Okay. So let's look at this next example, or this next thing. So I'm going to talk about the underlying idea that makes proof by induction work, okay? So we're going to assume that T is a subset of the natural numbers, and that 1 is an element of T, and that T is an inductive set. And that's all we need. Okay, that's all we need. T is a subset of N, 1 is in T, and T is an inductive set. And we want to use that definition of an inductive set to answer these questions. Is 2 an element of T? Well, think about it. What does it mean to be an inductive set? T is an inductive set if, or let's say, maybe we'll say it like this, provided if K is in T, then K plus 1 is in T. Okay, so here's what we know for this little example. We know that 1 is in T, and we know that T is an inductive set. Well, if 1 is in T, that means 1 plus 1 is in T. So yes, 2 is absolutely an element of my set. What about 3? By the same reasoning, it's an inductive set. 1 is in there, which means that 2 is in there. It's an inductive set, means if I add 1, 3 is going to be in there. So yes, absolutely an inductive set. And I think you see the idea by now. 4 is also going to be in there. So is 5, so is 6, so is 7, so is 8, and so on and so forth. As a matter of fact, it's not too hard to see that 1 also has to be in there. That 100 also has to be in there. And this is where that dominoes analogy kind of comes in. If you assume that when you knock down the first domino, it knocks down the second one, and that knocks down the third one, you're really assuming that if the kth domino is knock down the k plus 1, 1 will too. So eventually we'll knock down the 100th domino. So yeah, 100 is in T. So this is an interesting question to think about that I'm not going to tell you the answer to, because I want you to think about it, and you can look it up in the book if you want to. But will T be equal to the natural numbers? What does it mean for sets to be equal? They have the same elements. One is a subset of the other one. Well, we already know that T is a subset of the integers. Excuse me, T is a subset of the natural numbers. So the question you have to think about, are the natural numbers a subset of T? And you can do element chasing to do that, if you think that they are. Okay, and here are two more nice questions to think about. Can a finite non-empty set ever be inductive? Well, we've seen some examples where they weren't, but can there be a finite non-empty set that's inductive? And lastly, is the empty set inductive? Well, to answer part A, I'm not going to give you the full answer, but something to think about. A finite non-empty set is going to look like this. We'll say that it starts with 1, but if it doesn't, you can always just start something else. But eventually, we're going to have a largest element in there. Okay, last element or largest element. And for a set to be inductive, if n is in there, what about n plus 1? What has to be true about n plus 1 if we actually have an inductive set? So that's what you can think about. Is the empty set inductive? That's an interesting question. Think about what it means, or think about way back when we were doing conditionals, and we said things like, if x is an element of the empty set, then, then something. What kind of conditions could we say? Like, when is this true? When is this a true statement if x is in the empty set? So think about that. All right, spend some time thinking about that. Go back earlier in the book and look up when we did the empty set and truth tables, and in particular, the reason that the empty set is a subset of every set. Look that up, and I think if you do that, you'll be able to answer this question. All right, now, finally, we are at what is called the principle of mathematical induction. And it states that if T is a subset of the natural numbers, such that 1 is an element of T, that's the first assumption. And secondly, for every k in the natural numbers, if k is in T, then k plus 1 is in T. The conclusion is T is equal to the natural numbers. So that actually answers the question we talked about earlier. So again, write this down, drill this into your head. T is a subset of the natural numbers. If 1 is in T, and whenever k is in T, k plus 1 is also in T, that implies that T is equal to the natural numbers. Okay, now, we take this to be an axiom. That is, it's something that we just assume is true about the natural numbers. This is a little bit beyond the scope of this class, but I'll just say that depending on what formalization you take, this is either an axiom or it's something that is provable in the set of natural numbers. It just depends on how you build the natural numbers from set theory foundations. So that's all I'm going to say. But in this class, and in your other math classes at GGC or any undergrad college, or any undergraduate program, this is assumed as an axiom. Okay, so write this down somewhere. The principle of mathematical induction. And we use it to prove statements like this. We want to prove something of the form, for all n a natural number, some property holds. That is, we want to prove some property holds for every single natural number. That's when we use induction. Okay? And here's what we do. The first part is we prove that 1 is in our set T. That is, we prove that P of 1 holds. This is called the basis step or the initial step. That's the very first thing you do. You show that that whatever this property is, P of n, you show that it holds for 1, and you do your basis step. And after that, you move on to your inductive step. So this is the inductive step. You prove that if k is in T, k plus 1 is in T. In other words, we prove that if that property holds for k, it has to hold for k plus 1. And that's called the inductive step. The thing about induction is when you read it described like this, it seems strange and it may not make very much sense. But in practice, it's a whole lot easier to see how it works than it is to try to explain how it works. And when we do some examples, and even better when you do some examples on your own, it'll make a lot more sense. So again, to sum everything up, to prove that for all n and n, some property holds. Okay, so we'll see different properties. You do your basis step. You prove that it holds for P of 1. Then you do your inductive step. You prove that if this is true, then this is true. That is, it might be a little bit more explicit to say when you're proving it, what you do is you assume that pk is true, and then you show that pk plus 1 is true. Okay, so that's how you actually go about doing the proof. And if you're able to do that, the conclusion is this is true for all n by the principle of mathematical induction. So let's do the first example. So for each natural number n, 1 squared plus 2 squared plus ... out to n squared is equal to n times n plus 1 times 2n plus 1 times 6. Okay, now, first of all, why is this a candidate for mathematical induction? The property P of n is that for n natural number, that if I add up all of the squares up to n squared, I'm going to get this expression on the right. N times n plus 1 times 2n plus 1 all over 6. That's the property P of n that we're trying to prove. So let's see how this works. The basis step. I have to show that P of 1 is true. So what does that mean? P of n is the sum of the first n squares is equal to this. Well, if I have P of 1, I have the sum of the first square. That is 1 squared. And this should be equal to, n is 1 in this case. N is 1, plugging in a 1 on this side. So I have 1 times 1 plus 1 times 2 times 1 plus 1 all over 6. Well, that's equal to 1 times 2 times 3 over 6. Yeah, so the basis step checks out. Okay? And that's how you do your basis step. My basis step checks out, so I can move on to the inductive step. So for the inductive step, I'm going to assume that P of k is true. That is, I assume that 1 squared plus 2 squared plus ... plus k squared really is equal to k times k plus 1 times 2k plus 1 all over 6. And I need to show, whoops, not neat, I need to show that pk plus 1 is true. That is, I need to show that 1 squared plus 2 squared plus ... plus. Now, I'm going to write something that you might wonder why I'm doing it, but it's actually super duper important. I'm going to write my k squared right there, plus k plus 1 squared. This, I need to show that this is equal to what I get if I plug k plus 1 into that original right-hand side up here. This is going to be hard to squeeze in, but I'm going to do my best. K plus 1 times k plus 1 plus 1 times 2 k plus 1 plus 1 all over 6. So that is what we have to prove is true. So I'm going to go to a blank slide now to do this. So I have for my inductive step, I've assumed that 1 squared plus 2 squared plus ... plus k squared is equal to k times k plus 1. This is getting so ugly, I'm sorry. Let me try that again. K times k plus 1 times 2k plus... my iPad is stuttering. I don't know if it's going to show up in the video or not. Plus 1 all over 6. Okay, so that's what we're assuming is true. And then we have to prove the other thing. So let's look at 1 squared plus 2 squared plus k squared plus k plus 1 squared. What is this? How can I manipulate this into what I want? Okay. Well, look at these first terms. This, we already know something. We have assumed something about this. We've assumed this is equal to all of this. This is where we're using our inductive step. So this is going to be equal to k times k plus 1 times 2k plus 1 all over 6. But look, I still have this much plus k plus 1 squared. And now it's just a matter of algebra. Okay? I'm going to move all the way to the left for the sake of space, but this is going to be equal to, what I'm going to do is get a common denominator between these two parts, because I'm just using algebra to turn this into what I want. So this is going to be k times k plus 1 times 2k plus 1 over 6 plus 6 k plus 1 squared over 6. Okay, well, what do we do with that? This is going to be equal to k times k plus 1, 2k plus 1 plus 6k plus 1 squared all over 6. And now we just see what we can factor out. I can factor out k plus 1. So this is k plus 1 times k times 2k plus 1 plus 6 all over 6. I think I want to, let me move this up, and then I'll move this up. So this is equal to k plus 1 times k plus 2 times 2k plus Let me see real quick. Let me do some algebra. 3 over 6. This is what I wanted. Okay. Now, going from here to here, figure out why that's true. This is just some algebra. All I did was do some algebra to turn this into this. So figure out why that's true. Okay? Let's see. Let me set this up so I can slide everything up and then talk about why this means we're done. Okay? We originally said we wanted to show that 1 squared plus 2 squared plus k plus 1 squared was equal to k plus 1 times k plus 1 plus 1 times 2 times k plus 1 plus 1 all over 6. And so what I'm saying is that these are the same thing. And I think it's clear that they are. So that means we're done. We have proven that if we assume that the property holds for k, it also holds for k plus 1. So to sum this up, don't want to use that color. I'll just use the B. I'll just leave the B as red because it looks kind of neat. By the principle of mathematical induction, or you can just write PMI, by the principle of mathematical induction, 1 squared plus dot 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 plus n squared is equal to n times n plus 1 times 2n plus 1 over 6 for all n a natural number. And so that's the end of the proof. And I know I didn't formally start it as a proof because I didn't want you to get distracted, but that's how you do it. And I'm going to do another example or two before I set you loose to do homework problems. Before I do the next example, I want to quickly review some summation notation stuff. You've probably seen this before in some of your calc classes, but this is going to be a little bit more general and something that we will hit on again probably when we cover the sections on functions. But here's the idea. We start out with two integers, m and n, where m is smaller, okay? And f is a function whose domain contains all the numbers between m and n. All that means is f is a function defined on m, defined on n, and defined on everything in between. We can have this expression right here. The sum as j goes from n to n of f of j. All that is just the function starts at m, where my summation index begins, and goes up to n. So it's f of m plus f of m plus 1 plus f of m plus 2 all the way up to f of n. And then if n happens to be bigger, we can define something called the empty sum. It's not really relevant, just something to remember because it may come up in I think probably analysis 2. Real analysis 2 is when you would cover stuff like that. We're going to do an example next using summation notation in a little bit more familiar way. Okay, so this is the example that I want us to look at. I want to take, well, first I want to erase that little scribble, but I want to do this example. That the sum as j goes from 1 to n of j is equal to n times n plus 1 over, n times n plus 1 all over 2. Now there is a super cute story about Gauss discovering this when he was an elementary student. and he it's probably apocryphal. That is, it's probably not true. But I think usually whenever I teach induction, I always tell the story, but it won't have the same punch like this. So what I'll probably do is try to find a link to it somewhere and let you read it that way. But this is what we're going to try to prove, okay? So, sorry, I didn't say, I wasn't specific enough. We're going to prove that this holds for all natural numbers n. Okay, so because this is a proof that involves something true for every natural number, that's a pretty good indication that you're going to use proof by induction. Okay, so we will prove this by mathematical induction. And I'm not going to be super picky about the way that you write this out. I just want you to get the at this point, we've kind of moved past making sure your proofs are all written technically perfectly correct, and I want you to get these concepts. That's the most important thing right now. I am still going to make comments on it if you write something that might not be the best proper way, but I'm not going to take points off of it, or at least I won't take many points off for it at this point. So here's how one way you could do this, basis step, and I'm just going to write it in right here and check it. The basis step says that the sum as j goes from 1 to 1 of j, but that's just equal to 1. That's all that is. That should be equal to 1 times 1 plus 1 over 2. But yeah, that's equal to 1. And so the basis step checks out. So now we have the inductive step. Assume for k that the sum as j goes from 1 to k of j is equal to k times k plus 1 all over 2. Now, at this point, it might be a little bit better for you if you no longer use that summation notation. So I'm going to write it out like this. That is, we assume that 1 plus 2 plus 3 plus ... plus k is equal to k times k plus 1 all over 2. Or you could leave it in the summation notation, whatever you want. But in the time I've been teaching this, I've found that people can follow it better when it's written out like this. And this is going to be similar to the other example that we just did, but even a little bit easier. Okay. So let's see. Why don't we shrink this down and move it up here in the corner, because I still want to refer to it as I finish the proof. And I'm going to block this out so that I won't touch it. Okay. So we have assumed this. We have assumed that this is true. And now, let's not use red, let's use blue. Now, for k plus 1, 1 plus 2 plus ... plus k plus 1. Well, that is equal to the first k terms are equal to this. That was part of the inductive step. It's what's called the inductive hypothesis, actually. So I can write this as k times k plus 1 divided by 2. but I still have that k plus 1 term. So this is plus k plus 1. And now it's just a matter of algebra, okay? Even less algebra than we had in the other example. So this is equal to, get a common denominator, would be 2 over 2, and then combine them all together, and we'll have k times k plus 1 plus 2 times k plus 1 all over 2, which is equal to k plus 1 times k plus 2 all over 2. Okay, now let me move this over here. I really hope this isn't getting too messy. And let's think about what we just did. We showed that if we, first we showed the basis step, that 1 is in there. And then we assumed that this property held true for k. And then we showed that if we assume it holds true for k, it has to hold true for k plus 1. Because look at, let me use a different color, compare this expression with this expression, and I want you to think about what you would get if you plugged in k plus 1 for n. Okay, and that's what you would get. So what we say now, by the principle of mathematical induction, the sum as j goes from 1 to n of j equals n times n plus 1 over 2 is true for all n a natural number. And that's the end of the proof. Now we're going to do one more example that is not a summation example. It is instead a divides example. Now, before we write out the proof, we're going to do some sketch work for this one because it's not quite as straightforward as the other ones that we've been looking at. Okay, so the sketch work is going to be, I'm going to write down what the basis step is going to look like and what the inductive step looks like, and just kind of get an idea of where I'm trying to go before I get there. Okay, so the basis step, or P of 1, says that 3 divides 4 to the first power minus 1. Well, this one's clearly true because this is equivalent to saying that 3 divides 3. Well, we know that that's true. Okay? And then for the inductive step, P of k, what does P of k look like? What does this property look like at k? Well, it says that 3 divides 4 to the kth power minus 1. And then P of k plus 1, that says that 3 divides 4 to the k plus 1 minus 1. And it is not immediately obvious how to go from P of k to P of k plus 1. Okay? Let's see. Well, we know that if 3 divides 4 to the k plus 1, that means we can write 4 to the k, excuse me, I said that wrong. If we know that 3 divides 4 to the k minus 1, that means we know that 4 to the k minus 1 is equal to 3 times m, where m is some integer. Okay? And remember, this is what we want to prove. Okay? We want to show that this property holds. That is, we want to show that 4 to the k plus 1 minus 1 is equal to 3 times, I don't know, say L, where L is an integer. Okay, so I didn't do it on the previous example because I wanted to show you other ways that you could write out these proofs. But a good idea and a good habit to be in when you're starting out proofs by induction is to write down what P of 1 is. That is your basis step. Write down what P of K is. Remember, this is what you're allowed to assume. Okay? This is assumed. Whoops, don't want to do a highlighter. Let me backtrack that. This is assumed true. Okay? P of K is assumed to be true. So this is where you get something to work with by assuming this. And this is where you want to end up. Okay? So before you start doing anything, write down check out P of 1, make sure it works, and then write down what it is you've assumed, all of this, and then write down what it is you want to show. And maybe you could work from that to figure out how to get where you want to go. Okay, let's see if we can kind of play around with these to figure out how to go from here to here. So we've assumed, whoops, don't want to use red. I'm going to reserve that for the special stuff. We've assumed that 4 to the k minus 1 is equal to 3 times m, where m is an integer. Okay, this is what we have to work with. And we want to show that 4 to the k plus 1 minus 1 is 3 times L, I believe we used. Okay? So how do you get from one to the other? That is always the question for induction. How do you use your assumption to get where you want? Well, maybe you're going to notice that 4 to the k plus 1 is just 4 times 4 to the k. That is a useful fact that we may want to use. Let me use this ugly green color. It's like radioactive green. So how can we use that? Look up here. What we can do here is we can just rewrite this as 4, let's just go with green. 4 to the k equals 3m plus 1. Well, I want to get to 4 to the k plus 1, but that's just 4 times 4 to the k. So maybe multiply both sides by 4 and get 4 times 4 to the k equals 4 times 3m plus 4 times 1. That is 4 to the k plus 1 is equal to 12m plus 4. Well, that is, whoops, bear with me while I group everything together. Nope, bear with me while I group everything together. And now I can slide all this up. So how does this help us? Well, remember, we're trying to get to that 3 divides this. That is that 4 to the k plus 1 minus 1 can be written as 3 times something. Okay, so let's do this. 4 to the k plus 1 is going to be equal to 12m plus 3 plus 1. Why did I get that 1 out? Because I need it on the other side. Okay, but now everything on the right-hand side has a factor of 3 in it. And so what have we done? We have shown by that magical thing known as closure that 4 to the k plus 1 minus 1 can be written as 3 times an integer. So this is L, that integer L. So in other words, 3 divides 4 to the k plus 1 minus 1. And so what I would like you to do is to turn this sketch into a proof. That is, I want you to turn all of this that we did. Okay. Let me make that a little bit prettier. And pull this over here. Turn this, that was what we ended up with. Turn this sketch that we have into an actual proof by mathematical induction. Okay? And then maybe at our video session, regular ones, or you can email it to me, or you can show it to me if you don't feel confident with it. But turn this into a proof by mathematical induction, and see how that works out for you. Now, it is really important now more than ever for you to be reading along in the book. You know, at the beginning of the semester, I posted links to the extra videos in addition to these to look at. But for this section on mathematical induction, please read through the book. I think you'll find it very, very helpful. So that's all I have for this. I may do another little mini lecture about section 4.2, extended math or other forms of mathematical induction. Literally just like 1 or 2 examples of how that works, so that you will have seen them. But after this, I believe we're starting functions next week. All right, I'll see you online.